Okay. We are canonically 1 minute late, which I think is okay. I'm very glad to introduce Cecilia Tokman from the University of Queensland. Her talk will be titled Universal Gap Growth for Lyapunov Exponents of Perturbed Matrix Products. Thank you very much.
Thank you for the introduction, and I would like to take this opportunity to thank the organizers for the invitation. It really is a pleasure to be here at this fantastic conference. It's actually my second time in Brazil, and I also want to thank the hospitality of Catherine and Lorenzo, who are allowing me to stay here for a bit longer. And what I want to tell you about today is joint work with Jason Atnip from the University of Queensland, Gary Froiland from UNSW, who is also here in the audience, and Anthony Quas from the University of Victoria in Canada. And yes, this is about gaps in Lyapunov exponents. So we start with a question. What happens if we're given some noisy approximations or observations of a D by D matrix cocycle? What can we say about growth rates of vectors when we multiply them by this sequence of, say, perturbed matrices? Okay, so in general, we're going to be thinking about cocycles, so where these matrices come from some sort of ergodic process, but our results also apply in the case of time-dependent systems or just non-autonomous systems. So we'll say a little bit more later, but let's say just we start with a sequence of matrices A1 through A2, etc., and we have some small perturbations. So what can we say about the growth rates of vectors under this multiplication? So before telling you what we actually do, let me say a few words about motivation. So why do we care about this? And let me mention two examples. So the first one is, I believe, the favorite of the audience, which is the derivative cocycle. So in this case, we have a map, say a smooth map of a manifold. And so the derivative cocycle would be obtaining by multiplying matrices, which are just the derivative of this map along the orbit. Okay, and well, why do we care? Well, for example, this is related to, the Lyapunov exponents are related to hyperbolicity of this cocycle, and also, of course, when the top Lyapunov exponent is positive, we say or think of this as a chaotic system. Okay, so that's the first example. I believe everyone here is very familiar with this one, but the second example is one which has actually motivated quite a bit of the research that we've been doing in the last few years, which is the transfer operator cocycle. So yesterday in Daniel's talk, we heard about the transfer operator in the context of a single map. Okay, so when we have a map with some nice properties, for example, expanding, and we want to understand the long-term behavior, statistical behavior of this map, if we have some nice functional analysis setting, in general, I mean, this operator is infinite dimensional, but under some conditions, we can understand quite a bit about the dynamics of the map by understanding the spectrum of the transfer operator or some variations. So we can study invariant measures, decay of correlations, limit theorems, large deviations, a number of aspects of the dynamics. But if instead of looking at the composition of a map with itself over and over, we're in the context of a non-autonomous dynamics, for example, we're composing maps T1, T2, T3, for example, coming again, maybe the most typical way of thinking about this could be from an IID process, but there could be other ways of composing maps. For example, when we have some external driving, some, say, quasi-periodic forcing giving us this actual sequence. Well, instead of having the spectrum of the transfer operator, we could try to understand the Lyapunov spectrum and the associated ocellated splitting. And this will tell us quite a bit about, again, the long-term dynamics in this system. So in this case, Lyapunov exponents tell us about decay of correlation, in this case, quench decay of correlations. The associated oscillated splittings can tell us about stationary measures or invariant measures in the appropriate sense. And also, we can try and understand coherent structures or other nearly invariant regions of the dynamics by looking at other elements in the oscillated decomposition. So, but in general, this is an infinite dimensional operator, and this talk will be in finite dimensions. So let me just tell you one way in which these transfer operators can be approximated for matrices, by matrices. And this is the so-called Ulam scheme. This is just one way. And this idea goes back to Ulam, who is the same who came up with the idea of Monte Carlo simulations. So maybe you'll see some connection here. So the idea, Ulam's idea is somewhat simple to describe. So if we have a system, for example, say time one map of a vector field, say on the square, if we want to approximate this map by a finite dimensional, in a finite dimensional way, we can try to approximate it with the Markov chain, and for that we can just discretize the space, say in this case in 16 bins. Those bins will be the states of the Markov chain, and to encode the transition matrix of this Markov chain, what one can do is seed lots of trajectories in each of the bins and compute the proportion of trajectories which move between bins to give rise to a stochastic matrix that one can associate with Markov chain. So in this case, for example, if trajectories start in bin 1, in one step, say they can only remain there or move to bin 2, 3, or 4. And so the resulting matrix will have lots of zero entries corresponding to all the other elements there. So these, in general, are sparse matrices, so they are kind of good for, say, if one is going to do numerics with them. Of course, this is very naive, and one could try to refine the approximations by, say, refining the binning or adding more trajectories, but it will always be a finite dimensional approximation to the dynamics, or in particular to the transfer operator, which is surprisingly more informative than perhaps one would expect initially. Okay, so these are just two types of examples where we could be interested in understanding the Lyapunov exponents, and in particular, we also are interested in knowing what can happen when we have perturbations of the system. So let me tell you a little bit about what can happen when or what is known about stability, or how these, say, Lyapunov exponents and associated oscillated splitting, how they change when one perturbs the dynamics. And for this, we're going to be focusing for now in the context of random dynamical systems. So we have heard already in a few talks, the first talk yesterday by Stefano, also this morning in Francois' talk. So random dynamical systems will be systems when there's some external driving that is dictating us how we are going to be, say, multiplying our matrices or composing the maps that we are interested in. So in this case, it will be finite dimension. So we are going to have a driving system. So usually we assume ergodic, invertible, measure-preserving map sigma of a probability space. And to each element of omega, we associate a linear map or a matrix in this case, and we'll be looking at compositions or products of those matrices along the trajectory. And if we introduce perturbations, say at the level of the matrices, we keep the driving system unchanged, and we introduce perturbations. So what is known about stability. And let me just say here that one of the most studied examples is when sigma is shift and omega of, in some sequence space, and P is, say, a product of probability, so that corresponds to IID selection of matrices. But it can be much more general. So for example, sigma could simply be an irrational rotation or some other ergodic system. So there's quite a bit known about stability, for example, of invariant measures or stationary measures. And there are some experts actually in the room, but this is just kind of the top space associated to this decomposition, okay? And our questions are more about the whole spectrum, so all the Lyapunov exponents, for example, or the associated oscillated spaces. So what's known in that generality? So one of the first results is about stochastic stability of Lyapunov exponents for invertible matrix cocycles. So this is a result by Ledrapier and Young in the 90s, which we extended with Froilan and Quast to the context of non-invertible matrices and then some infinite dimensional matrices. Then there's also some relation. So it's known from the works of Ox and also more recently Bacchus and Poletti that stability of Lyapunov exponents is equivalent to stability of oscillated splittings in some sense. And there are also results about stochastic stability in the case of uniformly hyperbolic cocycles. So that's, again, some work due to Bogenschutz and more recently to Krimins. And that, for example, can be used to understand stochastic stability, so small random perturbations of a non-random map. And, well, this is not exactly the same context, but I think sufficiently related to mention it. So last year it was announced that there's proof of continuity of Lyapunov exponents for IID matrix products by Avila, Eskin, and Viana. So quite a bit, I mean, quite a few results. It's still not, I would say, quite a few open questions about stability. It is expected in general to have stability results. And by stability, of course, we mean that if we perturb the matrices or the cocycle a little bit, we're going to get small perturbations of the Lyapunov exponents in this case. But it's well known that there are also some examples of instabilities. The first one is written by Kiefer but attributed to Furstenberg. And it's this example where one can have a matrix with one stable direction, one unstable direction. And if one allows just a small probability of multiplying by a matrix which exchanges these two directions, one can get the Lyapunov exponents to collapse to 0. Okay, so this is the first instability result. Then this was also proved to apply in the context of volume-preserving diffeomorphisms. So, and this is an example, again, the idea attributed to Magnet, but published by Bocchi and Viana, and showing that away from uniform hyperbolicity, generic C1 perturbations of volume-preserving diffeomorphisms have 0 Lyapunov exponents. So one can start with non-zero Lyapunov exponents, and arbitrarily small perturbations will make the Lyapunov exponents collapse. And another example I want to mention in the context of transfer operators, it's a more recent result with Anthony Quast about random composition of analytic expanding maps. So I will just show you what can happen with the Lyapunov spectrum in the context of transfer operators. And for this, we're going to be working in, again, the simple setting of IID composition. So we're going to have two maps. So here they're written in complex form. So the first map is the doubling map. So we can think of this as expanding map of the circle. The other map is, again, maybe some recognize this as a Blaschke product. There's some experts in complex analysis in the audience. So this would be a Blaschke product, but it's expanding on the unit circle. So again, an analytic expanding map of the circle. And the randomness here would be that we are composing B0 with probability P and B1 with probability 1 minus P. Okay, so we compose this, and so this gives rise to a Perron-Frobenius or transfer operator cocycle. And we have, so we were able to understand the Lyapunov spectrum of this cocycle in, for example, show that there is what we call a phase transition. So when P is less than a half, when the probability of the doubling map is not too big, we have that this random dynamical system has what we call a complete Lyapunov spectrum. So the Lyapunov spectrum for that transfer operator cocycle consists of non-negative multiples of a number lambda. So lambda is some negative number, some finite negative number. And yeah, we actually understand some more about this, decomposition. Maybe we can say more at some point, but 0 is always a leading Lyapunov exponent, and all the other Lyapunov exponents have multiplicity 2 in this case. But as soon as P is at least a half, we get that the Lyapunov spectrum is trivial. So we only get 0 as a Lyapunov exponent, and this is related to the invariant measure or the stationary measure for the system, and it's also related to the fact that there's super exponential decay of correlations in this case. So that's the phase transition, but we also have what we call the phenomenon of collapse. So, and let me illustrate in this case with the examples with normal perturbation. So this would be corresponding to applying the map and then adding some normal noise with, say, variance epsilon squared. This also works if the noise is uniform, for example, and this phenomenon could also be achieved just by perturbing through Blaschke products, but let me just show it in this context now. So for normal perturbations, we can get that for P starting at a quarter, we get a trivial Lyapunov spectrum. So that means that in this interval, when P is between a quarter and a half, we have that when we have no perturbation, we get a complete Lyapunov spectrum, but as soon as the perturbation is turned on, the Lyapunov spectrum collapses. Okay? So that's just to give an idea that these instabilities can happen even in relatively natural models or relatively natural situations that we may want to understand. But the rest of the talk will be focusing on the question of simplicity of Lyapunov spectrum. So the Lyapunov spectrum is called simple if we have d different Lyapunov exponents in the case of d by d matrices, or similarly when the dimension of each of the oscillated spaces is 1. And there are several works investigating simplicity of Lyapunov spectrum. So some of them were already mentioned by Francois earlier today. There's also a strong Brazilian connection. So there are several names here. So Avila and Viana showed the Sorich-Kontsevich conjecture. So also Mateus, Duarte, Klein, Poletti, Baques, Barandas, Lima. So there are several names, several people who have worked in different aspects of this problem. And there's actually recently work by Gorodetsky and Kleptsin showing that even in non-stationary settings, one can have, one can do or use Furstenberg theory to show simplicity of Lyapunov spectrum. So in most of these works, not all of them, but most of them, they use this Furstenberg theory. And so it's a way of getting simplicity, but there's no quantitative information. So no information on how far the Lyapunov exponents are after the perturbation. So they're different, but that's it. So what we'll be talking about is quantitative bounds. So what can we say about the separation between these exponents? So the setting will be the following. So we are in dimension D. We're going to be looking at a sequence of matrices. So A1, A2, etc. So we only suppose that this is bounded, for example, in the L2 operator norm. The bound, let's say some number k, it doesn't really matter what it is, and without loss of generality, we can assume that this is 1. So if we just divide everything by k, nothing in what I'm going to say changes, but of course we can, for example, study hyperbolic matrices if we want, or other, I mean, it's just a normalization here that we're going to be assuming the norms are bounded by 1. So we're going to look at perturbations. So what perturbations do we have? So we are going to add to each of these matrices a small constant epsilon times this matrix psi I. So psi I will be a sequence of IID matrices where the entries are IID distributed uniformly. Okay, so this uniformity is not so important. This would also work if we have, say, upper and lower bounds on the densities for these perturbations, and I will say a few more words about other types of perturbations there. And so we'll be interested in these matrix products A epsilon n, so we're using cocycle notation there to just denote the product of the first n matrices along this sequence. So before telling you about the results, let me make a comment. So we are not assuming there's stationarity in the sequence, so we're just taking a sequence of bounded matrices. So what, I mean, there's no multiplicative ergodic theorem to give us Lyapunov exponents. So let me just make the following comment. So we'll be talking about singular values of the matrices. And these were already introduced in the talk by Pablo. So these are, if you want, the square roots of the eigenvalues of A times A transpose, or another way to think about them is these are the semi-axes of the ellipses, which are the image of the unit ball and their multiplication by the matrix. So let's call Sj the jth largest singular value of the matrix A. And we have a lemma here saying that if we have an arbitrary sequence of bounded D by D matrices, and we have epsilon greater than 0, if we fix J and K between 1 and D and look at the quantity which is the liminf of 1 on n times the logarithm of the quotient of the jth and the kth singular values for this matrix A epsilon n, so this quantity is constant almost surely, okay? So even if the A's are just a sequence of matrices, they don't come from a stationary process. This is just a consequence of Kolmogorov 0-1 law and simple properties of singular values. So we're going to be referring to this number as the gap between the jth and the kth Lyapunov exponent. So even though this is some abuse of notation perhaps, but this is always, this is almost surely constant. And that's the quantities that we will be studying. So let me tell you the results that we have, and then I will try to give you an idea of the strategy and the proofs. So the first result is for 2 by 2 matrices. So if we have a sequence of 2 by 2 matrices, and if we have epsilon between 0 and 1, we have a constant which just depends on epsilon. so that for any sequence of 2 by 2 matrices of norm at most 1, the gap between the first and the second Lyapunov exponents is bounded below by this constant. And in fact, we can give some bound, so we can say that this constant C2 is at least this exponentially small quantity, so exponential of, for example, -1 on epsilon to the 35. So let me say this is not optimal at all. We have not tried to optimize these bounds. Our emphasis here has been on universality. So this bound applies regardless of the sequence. And of course, it's most interesting perhaps if we start from the case where the Lyapunov exponents are the same. Okay, so if the cocycle is already uniformly hyperbolic or something, I mean, it's really not adding much there. But when we start with equal Lyapunov exponents, this is telling us a lower bound on the separation after this perturbation. The second result is somewhat similar, but for 3 dimensions. So in this case, we have another constant C3, so that the gap between the first and the second Lyapunov exponents of these perturbed cocycles and the gap between the second and the third Lyapunov exponents of the perturbed cocycles are bounded below by this constant, and this is an even smaller quantity, exponential of -1 epsilon to the very high power. And again, the emphasis is on universality. Okay, so we have that the Lyapunov exponents are not only simple, but with these quantitative gaps. The third result is about just non-trivial spectrum. So we have, for any dimension, some constant C prime D, which only depends on epsilon, so that if we start with a sequence, bounded sequence of D by D matrices, and we look at the gap between the first and the last Lyapunov exponent, we're going to get lower bound, a universal lower bound that we can write bound from below by this exponential that depends on epsilon and on the dimension. So at least not all the Lyapunov exponents are the same. If we have some more structure, for example, if we start with orthogonal matrices, we can do better. We can get, so if we have D by D orthogonal matrices, then there is some constant which actually only depends on epsilon and is independent of the dimension, so that the gap between the J and the J plus first Lyapunov exponents is at least this exponential of -1 on epsilon to the 2 plus a little bit. And here the comment is that if the perturbations instead of being uniform are given by normal perturbations, this is a case which has been studied in detail by Bednarski and Quas, where they showed the optimal bound. So the gap is of order epsilon squared. So you see, this is not optimal, the one that we obtained. The optimal one in the case of normal perturbations is epsilon squared, and they actually also can tell us the coefficient. And it is what we expect. If we were trying for optimality, we would be expecting something like this. But again, we are just thinking of universal bounds for the moment. It's the first work in this direction. And the last result is about D by D matrix. So what can we do in the general context? So we can show that there is some number, CD, only depending on the dimension and epsilon, so that for any sequence, bounded sequence of D by D matrices, the gap between the J and the J plus first Lyapunov exponent is bounded by this constant CD of epsilon. And the difference between these results and the previous ones is mostly that this is just existence of some bound, and we don't give some specific information about what this quantity could be. Just existence, just abstract universality. Okay, so let me now try to give you an idea of how we go about proving this. And the first theorems, we follow this strategy, so there's 4 steps. The first one is non-singular initialization. We're not assuming that we start with invertible matrices, so that will be the first step. Then we'll have some triangle inequality, and gluing lemma, and some bookkeeping. So let me tell you what this is about. So the first step is just to make sure that we can perturb away from non-invertibility. So this is a simple lemma saying that if we start with a matrix of norm at most 1, we can perturb by change by at most epsilon on 2 and get a new matrix which is bounded, say, by 1 minus epsilon on 2, and whose dth singular value is at least epsilon on 2. So it's non-singular and in some controlled way. And this is, just a simple lemma which can be proved by just looking at this singular value decomposition, or also called polar decomposition. So the next step is what we call the triangle inequality for target blocks. So let me introduce a couple terms. So we're going to call a target matrix A in D by D if it has a norm at most 1 minus epsilon on 4, and the dth singular value is at least epsilon on 4. Okay? And we're also going to be talking about near identity perturbations of a matrix. And by this, we will mean that we are multiplying the matrix either on the left or on the right by another matrix which is close to the identity. So it's the matrix and the inverse are close to the identity. So the triangle inequality lemma is the following. So if we have number n, which we'll be calling the block length shortly, and 2 numbers m and m prime in between 1 and n, as well as target matrices am through am prime. So we have a sequence of matrices satisfying these nice properties here. Then if we perturb these target matrices entry-wise a little bit, so there's a bound on how much we can perturb the entries depending on epsilon, the block length, and the dimension. If this is sufficiently small, then we can control exactly how much we lose in the ratio of, say, the jth and the kth singular vector for the perturbed block, a multiplication of am through am prime of the perturbed system, and the ratio for the target matrices. Okay? And so we lose at most a factor of 1/2. So this is an inequality which will allow us to transfer, say, what we know about what happens near target matrices to some small neighborhoods. And of course, this we can give some quantitative information. So there's a number p which we can be really explicit about in terms of epsilon, the block length, and the dimension. So p is a number between 0 and 1, so that for any target sequence am through am prime, if we want, so the probability of observing perturbations within the range, the allowed range, is at least given by this p. Okay, so it's not so important what p is, but it can be computed explicitly, and it will come up shortly. So more to the core of the argument, we have what we call a gluing lemma. So this is, for this, we look at this function which depends on 3 matrices, so left matrix, A, and right matrix. And it tells us the difference between the logarithm of the ratio between jth and kth singular values for the whole block LAR and the sum of the logarithms of the ratios of the jth and kth singular values for the left matrix and for the right matrix. So in a sense, it's allowing us to measure how far we are from, say, additivity or, so from having an additive process. And the result here is that there is some constant, so again, independent of, so just depending on the dimension, so that if we have any invertible matrix L and R and any matrix A bounded in norm by 1, if we look at the probability that this function, that this, say, gap is more than x, this probability is bounded by some constant times some exponentially decaying quantity times 1 on epsilon. Okay? And this, here, these perturbations are really the ones that we were considering before. So just IID perturbations on each entry. And as a corollary, what we get is that this random variable, the absolute values of these functions are uniformly stochastically dominated by random variable which is some constant plus an exponential. And so this has exponentially decaying tails, and so this allows us to get bounds on the expected value of f. So the lower bound is of the order of, well, 4 times dimension times log epsilon minus some constant which only depends on the dimension. So this is what this is the result that will allow us to glue our estimates on smaller blocks and transfer these to larger and larger blocks. And the final component of this of the strategy is what is called bookkeeping, or we also say we call this the meta theorem. So the hypotheses here are quite strong. So here we fix j and k between 1 and d. We fix some epsilon and some gap, which is at least 2. And what we assume is that there is some n, some block length, so that for any d by d invertible matrices M1 through Mn plus 1, there are some numbers m and m prime between 1 and n, and a target sequence of target matrices, which are near identity perturbations of our original matrices, so that the gap between the jth and the kth singular values for the products along this target sequence is at least the gap that we want. Okay, so that's all of that is hypothesis, and the conclusion is that then we can find a constant only depending on epsilon, so that for any matrix sequence, bounded matrix sequence, we get that the gap between the jth and the kth singular Lyapunov exponents are bounded below by this constant C of epsilon. And this constant is actually explicit in terms of the block length n and the probability p that we mentioned before from the triangle inequality. So, so just a couple comments here. So one is, I mean, we're assuming this is for every choice of gap, but in practice we will be applying it to some specific choice, and this is explaining some of the exponents that appear in our expression. So it's just so that you know where these exponents come from. And the second comment is, of course, to try and show this, to use this meta theorem, what we need to do is see that we are in the context of this result, which may be challenging sometimes. So how do we find these targets? How do we make sure we are in the context of this result? So what we basically split the blocks of matrices into two classes. So some are like good and some are bad. And so the good ones are the ones that we call spread. And the bad ones are the ones we call align. And the idea is that if we have a product of n invertible matrices, and we look at the singular vectors of this matrix product, let's say these are V1 through Vd, order in decaying order of singular values, and we look at the spaces spanned by the leading, say, j singular vectors and the smallest d minus j singular vectors, and we look at their images, ejn and fjn, and their evolution by multiplication, we look at the distance between these spaces, or the distance between norm 1 vectors on these spaces, and we call delta n the minimum of all such distances. And we call the block spread or eta spread if this gap is at least eta for every n, and otherwise we call it nearly aligned. And the reason this separation is useful is because in the case of spread blocks, we can, if we have an eta spread block, we can consider it a block length, which is specifically given in terms of the gap g, epsilon, and eta, and make sure that by applying near identity perturbations to the original matrices, we get target matrices with the desired gap separation. Okay? And this is because we can treat the directions basically independently and make things grow at the right rates. And in the case of aligned blocks, the situation is in general more complicated, but one thing we can say is that if we have a non-singular D by D matrix and we have two orthogonal vectors which get mapped very close under the multiplication by B, then we're going to have a separation between the first and the last singular values of that matrix. Okay, so at least this will allow us to show the first two theorems, which I remind you here. So, sorry, the first and third theorem. So the third theorem is about non-trivial spectrum. And of course, the first theorem is just a direct application of the third theorem to the case of 2 dimensions. So how do we finish the proof of that, of those theorems? So the idea is to consider a block of length, something like g log g on epsilon. And if we look at a block of that length, then we can always find m and m prime and a sequence of target matrices mm through mm prime of near identity perturbations with the desired gap in the first and dth singular values. And so we are in the context of the meta theorem. We can apply that, and so we can conclude. I mean, these are just some constants, but the conclusion is that we can find this universal separation, this universal gap in terms of epsilon and the dimension, as was stated. And in the case of d equals 2, this gives the exponent 35. I will skip the proof of the second theorem. If anyone is interested, of course, we can talk about it, but it's just more work to deal with the nearly aligned case. The theorem about orthogonal matrices, so this is a little bit simpler because we are in the case of spread vectors. So we start with an orthogonal frame, and that's preserved under multiplication by orthogonal matrices. And so the blocks are square root of 2 spread. And so that allows us to use our meta theorem with block length of 1 on epsilon plus a bit. And so that gives us the separation between all the Lyapunov exponents of this order exponential -1 on epsilon 2 plus a little bit. So that's the case of the orthogonal matrices. And the last result about universal bounds, the strategy is a little bit different. So let me use the last few minutes to tell you how we go about that case. So there's three main parts. So one is simplicity, then compactness, and the conclusion. So simplicity, this is just a statement about having simple Lyapunov spectrum without any quantitative control. And this is in the context of cocycles. So if we have a cocycle of bounded D by D matrices, and we look at perturbations of the type that we've been working with, the result is that, well, we have a separation between the Lyapunov exponents. So if we have this noise perturbation, we're going to get a simple Lyapunov spectrum. And the proof of this goes roughly along the lines of what I said before, but now we don't have any quantitative estimates. The next step is compactness. So this is can be thought, I think, as related to this Furstenberg correspondence principle that was mentioned yesterday. So if we have, we had the case that for some epsilon and for every delta, we are able to find a sequence of matrices, bounded matrices, so that the gap between J and J plus first Lyapunov exponents of the perturbed cocycle is less than delta. If we're able to do this for each delta, then that would imply that there is a shift invariant ergodic measure on the space of sequences of matrices that so that the jth and the jth plus first Lyapunov exponents coincide. So, so then the conclusion is just basically by contradiction. So if if for some epsilon between 0 and 1, and for some gap we are not able to find a block length, so that we're put in the setting of the, say, meta theorem, where we eventually get the separation, then we should be able to find arbitrarily long blocks of matrices, so that the perturbations would never produce any gaps between J and J plus first singular values exceeding the target gap. And by taking limits of these blocks, we would be able, using the compactness lemma, to find a collection of sequences of matrices, so that when we perturb any subblock, the ratio is J and J plus first singular values remain bounded, and so under perturbation we would get coincidence of these Lyapunov exponents. And of course this is in contradiction with the theorem about simplicity. So that's the proof of the universality of gaps in the case of D by D matrices. And let me actually stop here, and thank you for your attention.